Okay, welcome back. And so this is second lecture on games. And before going to evolutionary games, I would like to first tell you about repeated games. Okay, so last time we just discussed single stage games. And essentially the theory of repeated games is, so the setting is one where the players, they have a given payoff matrix for the game they play every day, but they play this game over and over again, okay? Say they play this game every day, okay? Say for a finite number of days, okay? So, let me discuss, so how are we going to discuss this? Okay, so first of all, so if there is a certain payoff matrix for each player, depending on the strategy he plays and the strategy that the opponents play, then this is for a single stage. Then the strategies are going to become a profile of strategies. So a strategy will be a vector that specifies at every time what the agent I is playing. And likewise also for the opponents, you are going to have these strategies, a plan of action for every player. And for the payoff, we are just going to say that the payoff of every agent is going to be the sum of the payoff that the agents get for every stage game. Okay, so let's first consider the case where the game is repeated a finite number of times, let's say t, okay? Now this problem becomes very, very complex because, say, imagine that the strategies of agents are just, say, two, like in the prisoner's dilemma, they are cooperate or defect. So there are two strategies at each point for every player. And so you could say, well, okay, there are 2 to the t possible strategies for the game repeated t times, okay? But that's not true because strategies in a repeated game are a function, can be a function of whatever other people played at previous times, okay? So Si of t is a function of whatever other people played at previous times. Now you can just do this calculation for a two-player game, each with 2 strategies, and you end up with with a number of possible strategies. If t is equal to 10, then the number of strategies is 2 to the 300, let me get the number right, 49,525. Okay, so this is 10 to the 105,000 and something, okay? So it's a huge number, Okay, so your state space, the space of possible, and you have to think that the behavior of, if you want to specify the behavior of both agents, then you will have the square of this, okay? So it's a huge number, okay? But again, you can think of looking at this huge matrix and finding the Nash equilibria, okay?
Can you please break it up into parts, like how do we reach 2 to the power that big?
Okay. So you have to think that, say, let's look at t equal to 2, okay? So t equal to 2, then you have that the strategy of player I at time 1 can be chosen just in 2 ways, okay? At time 2, it can be chosen at time 2, this will be a function of the strategy of the opponent at time 1, okay? So this can be either a plus or C or D. And how many functions of this type you have? You have 4 functions, okay? And you can go on like this, okay? So at t equal to 3, you should think about how many functions of 2 arguments you have, okay? And so there are this argument can take 4 values, so you have 2 to the 4, okay? You go up to 10, t equal to 10, and you get this number, okay? You have 8 functions, yes, yeah. Okay, so now let's consider the prisoner's dilemma, and let's see what happens if we take the prisoner's dilemma, where either you cooperate or defect. Let's say that I'll take payoff 0, 0 if they both cooperate, minus x and 1 if player 1 cooperates and player 2 defects, and 1 minus x, otherwise 1 and minus x in this case. So where x, you can think of x as the cost of cooperation. So you can think, say the cooperation means that I invest some effort, and this effort gives a benefit of 1 to the other player, okay? And so in this case, player 2 doesn't make any effort. He gets the benefit of player 1 who is cooperating, and player 1 just pays the effort, okay? Whereas if they both cooperate, each pays the cost, but also get the benefit from the other player, okay? So this is a simple interpretation of this game, okay? Now, if you repeat the game, say, 10 times, then you have to look at the Nash equilibrium in this huge table. And but you can figure out that essentially there is only one Nash equilibrium, okay? Which is always defect. And how do you reach this conclusion? Well, you do backward induction, okay? Backward induction means that you start from the last day, day 10, and you ask yourself, what should I do at the last day? Okay, it's just a single stage Nash equilibrium. I should play the single stage Nash equilibrium of the prisoner's dilemma. I should just defect, okay? Then what should I do at t minus 1? Well, given that I will defect tomorrow, then I should defect also today, okay? And so on, you can do backward induction until the t equal 1. And you see that the only Nash equilibrium is always defect, okay? Okay, so, and actually whatever is t, no matter how long we repeat this game, this is always going to be the case, okay? Yes. In what sense the best a bad choice? A bad or the best? What are you what did you say? The bad or the best? Yes. Is the optimal choice? It's a choice such that given what the other player does, no one has incentive to change. Okay? If you know that the other guy is playing always defect, then you should always defect. Because otherwise you're going to get a punishment. Okay? Now, however, if you this result relies on the fact that there is one day where we know, where both players know that the game is going to end. And, but imagine that there is no such day where players know that the game is going to end. Imagine that every player knows that there is a certain probability delta that the game will go on. There is a probability 1 minus delta that there will be no further game, okay? Then what happens in that case is that the number of times that we play, the two players play this game becomes a random variable, okay? And the probability that this, the number of times they play this game is larger or equal to t is equal to delta to the t minus 1, okay? Okay, where delta is the probability that every time the game is continued, okay? Now, you cannot apply backward induction. And actually what you see is a quite opposite result. That essentially there are many Nash equilibria. Actually, whatever payoff you want to reach in a certain region can be reached by a certain strategy, okay? So let me, so in other words, there is a theorem that is called Folk's theorem. It tells you that, well, in this particular case, if this is the payoff of player 1, this is the payoff of player 2, you have these 4, okay, this is 1, this is the point, say, yes, this is the point 1 minus x. This is the point minus x and 1. This is the point 1 minus x, 1 minus x. And this is the point 0. These are the 4 points of the possible payoffs in this table. You form this polygon. And essentially, Folk's theorem tells you that any there is a way to achieve any payoff pair in this region, okay? You give me the point in this region and I tell you this is the strategy you should play, okay? So let me give you the, in particular, there is a way to achieve this payoff, this payoff per game, okay, because now your expected payoff, now the utility function becomes your expected utility function. Here you should put what is the probability that the game number t will be played, which is the probability that is actually the probability that the number of games you play is larger than t, okay? And then the payoff of player of game t. Okay, so if so if this is your payoff per total payoff, there is a way to achieve this payoff at every stage of the game, okay? And what is this? How do you achieve this? With what are called trigger strategies. So imagine that the two players can talk to each other, and player one can say to player two, I'm going to start cooperate. I will go on cooperating as long as you cooperate. As soon as you defect, I will defect forever. Okay? So, so the strategy of agent I at time t will be to cooperate if s minus 1, s minus I at t prime has been to cooperate for all t less than t prime, or otherwise to defect. Okay? So as long as you cooperate, I will cooperate. But as soon as you defect, I will defect. Forever. Okay? Then let's call this trigger strategy T. Of course, I'm assuming that the two players can talk. And essentially, this talk is what is called a cheap talk, has no consequences in terms of payoff. And what the other opponent has to check is whether this is a best response of agent 1. Okay, if it is a best response of agent 1, then this is a credible, what the deal that he's proposing is a credible one. Okay, so in this, so you see, in this strategy there is a threat. So the player 1 is threatening player 2 to defect forever if he defects. And what player 2 has to check is whether this threat is credible or not. Okay? Essentially, how you do this? Well, player 2 has to check whether he better cooperate against this, cooperate forever against this strategy. That is to play also this trigger strategy, okay? And how much would he get? Well, he would get, if he cooperates forever, then he would get 1 minus x at every stage. So you just have to sum the geometric series, and you get 1 minus x divided by 1 minus delta. Okay? If instead you could think that player I could consider cooperating up to, or say, tau time steps, and then defecting forever. Of course, if you are playing against this strategy, once you defect once, you better defect forever. There is no reason why you should start cooperating again, because and you can compute this, and essentially is a sort of simple calculation, but if you do this, you get that this is 1 minus x minus delta to the tau delta minus x divided by 1 minus delta. Okay? This tells you that if the probability that we continue cooperating is large enough, then as soon as I defect, I will suffer a loss. Okay? So it is credible. Eh? Yes, so this means that the opponent is cooperating for tau time steps, and then is defecting forever. Okay? And so I took the same symbol T for the number of steps, sorry, but this is the strategy, this is this trigger strategy. Okay, so what this means, it means that if the guy is playing a trigger strategy, then I should always cooperate, but actually if I cooperate, that would not be credible for agent 1. So I should also play a trigger strategy, okay? So trigger strategy is a Nash equilibrium, and by this trigger strategy, what I achieve is a payoff of 1 minus x per game at every stage, okay? Now, you may ask yourself, how do I get a payoff like this one? Well, my deal could be, I will cooperate, I start cooperating, I will cooperate for 10 periods, then I will defect for 5 periods, then I will cooperate for 10 periods, and so on. And you better do the same, okay? And the guy checks, does the maths, and see, well, this is a credible threat. And then this is the game you achieve. And actually, you can see that the agent can also achieve a payoff which is larger than 1 minus x. The way in which you achieve this thing is by saying, well, the deal is the following. I will start cooperate. I will cooperate for 10 times. Then I will defect for x times, and you better cooperate. Because otherwise I will defect forever, okay? And you do the math and you see that this is actually best response. I mean, abiding to this deal is so these essentially all these every point here can be reached by one of these self-enforcing contracts. So one contract that specifies how the two players should play, and that every agent, every player has incentive to follow. Okay? Yes. Yes. So the contract says for this point here, for the first point here says here is delta minus x. So if you do the calculation here, essentially you get from these tau periods, you get a payoff of 1 minus x divided by 1 minus delta minus the continuation of the series, okay, which gives you delta to the tau of 1 minus x divided by 1 minus delta. And then you have that at this point here, the guy gets a payoff of 1, okay? Gets plus 1 times delta to the tau, and if you compute this, you get this. Okay? Which means say that if it is too costly to cooperate, then you don't cooperate. Okay? It must be either the prospect of playing this game again must be high enough, or the cost of cooperation should be low. And so, I mean, as I was saying, for each one of these points, you have a contract which is specifying what player one should do, what player two should do, what player one does if player two does not do what he proposes to do, and et cetera, et cetera. Okay? Because it is in his best interest. Yes, because, in this way, essentially, in this way, player two finds out that it is convenient for him to follow the deal, and in order to check that the deal is, the threat is credible, I mean, the way in which player one is threatening is by playing a Nash equilibrium. Okay, so this is already a Nash equilibrium. Okay, so that it is credible. So if because it's the best strategy that player one could do. Yes. So look, this is, in this particular case, this is the best response at every stage of the game, no? So that it is credible that player one will play the best strategy. Then the question is, maybe there could be, so against this strategy, player two could play a number of different strategies which would be a Nash equilibrium. For example, he could play a strategy called tit for tat. Tit for tat means I start cooperating, and then I will do whatever you did last time. If you defected, I will defect. If you cooperate, I will cooperate, okay? And you can show that even two players playing tit for tat is a Nash equilibrium. The tit for tat is a best response to this. And so that this Nash equilibrium is not unique. There are many strategies achieving a Nash equilibrium. So for example, so tit for tat is better than this because there is a notion of forgiveness. Okay, so maybe you defect once, but if you start cooperating again, I will start cooperating again. Okay, so indeed, there was this person, Bob Axelrod, that asked to several of his colleagues to provide strategies, and he did a tournament of the strategy proposed by all his friends. And what he found out that this tit for tat was the best one. Was the one who was accumulating a larger payoff when played in this game. Okay. So there are many strategies that achieve the same point. Okay. As a matter of fact, in equilibrium, when agents are playing the equilibrium, even if they're playing this trigger strategy, what you observe is just they always cooperate. You never observe a punishment. So you cannot, say, distinguish from the play of the game, what is the strategy that is being played, because you don't read the contract and what happens if someone deviates, okay? And, but I mean, this same thing of, say, in many society, people don't go around and steal because maybe they can be caught by the police. Maybe nobody's sure. I mean, I never do that because, I mean, so just, even if I didn't do it, I behave this way because I think this is what happened. Okay, so so in particular, what I wanted to stress is that you can also have this exploitation out of this in these repeated games. So a contract where someone say, well, I will cooperate for some time, then I will punish you for some time, and then I will cooperate again, etc., but you better cooperate forever, because otherwise, and so actually, you see, you can interpret these strategies in repeated games as social norms, and when you see around, you see a lot of, I mean, that this kind of description resounds with the social norms that we see around in societies. Okay, so now there's another interesting thing I want to mention briefly, is what happens when you have more than 2 players, okay? So let's imagine that you have n players. And let's imagine that the game is the same. So for a single stage, the agents can play 2 strategies. Si is equal to 1 means cooperate, and 0 means defect. And essentially, you can say that if player 1 cooperates, that is Si is equal to 1, then he pays a cost X. And in any case, he gets a benefit from all the other players who are cooperating. Okay? So all the other players who cooperate will give you a payoff of 1 to Mr. I. And if Mr. I defects, then he's going to pay X. If Mr. I cooperates, he's going to pay X. Okay? So again, the best response here is just to have S equal to 0, to defect. Okay? Whatever the other guys are doing. Okay? Is this clear? And now you can ask yourself, well, let's repeat this game for many, many times. And let's ask ourselves whether we can observe cooperation in this case, okay? And what happens is, so when you ask yourself this thing, I mean, so you have many agents, and the question you ask is, well, should this guy, how many people should this guy punish? So imagine that we use these trigger strategies, okay? So it means that every agent will cooperate conditionally on other agents, okay? But is it credible that a condition on everybody else? Or should the condition is play only on a few of the other agents? And also, if this guy conditions his cooperation on J, should J condition his cooperation on I or not? Okay? And you can ask these three things, and what you find out is that essentially a Nash equilibrium, when you take this delta going to 1, a Nash equilibrium of this game is where essentially you have groups of, when you have groups of M players that cooperate conditionally on each other, but this M is the largest integer, the smallest integer larger than X, okay? So M is larger than X and is less than X minus 1, okay? And why is this so? Because essentially, if imagine that there are C cooperators in the society, and Mr. I is cooperating, then his payoff is essentially C minus 1 minus X, okay? If he continues cooperating, okay? Now, if instead it affects, the number of people who cooperates will decrease by M, because M is the number of people who punish him, okay? So we'll go to C minus 1 minus M. But because this M is larger than X, then this will not be convenient for him, okay? So, but M, the number of people that he controls, should not be very large, because it's not credible that this M be very large. So you get this by thinking, well, imagine Mr. I is cooperating conditionally on these guys, and let's imagine that this guy defects, okay? Then if, and let's ask ourselves if Mr. I should punish him and stop cooperating, okay? So if this guy, let's say K, stop cooperating, and is not, and I is not cooperating conditionally to him, then his payoff is Ci minus 1 minus 1, which is the contribution he loses when this defects. But if I decides to defect and to punish K, then he will get C minus 1 minus M, where this so the number of, so there will be M people that also stop cooperating, and he will, yes, he will get also C minus 1 minus M minus 1. So if K is not conditionally cooperating on I should not conditionally cooperate with K, because essentially if I punishes K, then his payoff also will be less than if he doesn't punish him, okay? And also you can check that instead it is credible that I stops cooperating when J, one of the guy, he checks stops cooperating, because essentially this response is the best response if X is larger than M, because X is larger than M plus 1, okay? So you see that, say, if X is equal to 1, you have that in this society, cooperation is sustained by a couple of people. If X is equal to between 2 and 3, cooperation is sustained by triple, 3. If it is 4, etc., etc. So this tells you that the size of the group, the social groups that you find in this society is proportional to the cost of cooperation. The more costly is cooperation, the larger is the group, okay? And this, I think, is an interesting insight from game theory, because essentially also we observe in societies that society have grown more complex, and the cost of cooperation is going. There is this guy, Harari, who has written that our life as settlers is much worse than the life of hunters-gatherers, and because, but okay, so this is just an observation.
Hello.
Questions? Yes.
Sir, somehow I have lost in between some calculations. Maybe that's I want to clear something. First, the delta used there, that is the probability that the same two are interacting in the next round.
Yes, yes. Delta is the probability that the game will go on.
Between the same two.
Between the same two, yes.
Yeah. Now
in this case, between the same n.
Yeah. Now comes these things. That, for example, tit for tat. Okay.
Yes.
That is the thing that player 1 will choose in the next round what player 2 chose in the earlier round.
Yes.
My question is that this is something new strategy we are invoking. Then we are using calculation to show that it is coming to be an optimized strategy.
Sorry, can you repeat?
Okay. First, there was two strategy,
yes.
Cooperate and defect.
Yes.
That was my game. Now you are playing the game for repeated times.
Yes.
Then we are invoking one new strategy named tit for tat.
Yes.
Now we are doing some calculation and showing that it will may come out as an optimized strategy, tit for tat.
Yes.
From the player point of view, they did not know tit for tat. They only knew cooperate and defect.
Yes.
I'm just asking whether they are doing the calculation first and then choosing tit for tat, or it is coming out automatically in a natural way.
Okay. Okay. So this goes back to what we were saying at the beginning. So how you come to find out a strategy is either by, say, thinking strategically, that essentially a particular strategy will be a Nash equilibrium strategy, and then it should also be the best strategy that for the other player, and so on. Or, as we are now going to discuss when we discuss, say, evolutionary games, it's just something that it is encoded in your behavior. So you, I mean, there is a population, and there are some individuals that behave this way, some individuals that instead behave in a different way, and those individuals that happen to play a best response to the strategy of others, they will get a higher payoff, which means that they will reproduce faster than others. Okay? So how you get the players to say to understand which is the best strategy, that is not something which is discussed in game theory. Or so it's once you discuss Nash equilibrium, you just care about making sure that which strategy is a Nash equilibrium strategy, which pair of strategies are Nash equilibrium or not. Now here, the strategies are not like action, like cooperate at day 10 or defect at day 10, etc., etc. They are plan of actions. Okay? They are behaviors, if you want. Okay? Actually, they are conditional behaviors. They are behaviors that depend on. So this strategy here, you see, is it's a conditional behavior. It depends on what the other guy does. Okay, so it's a function.
Yeah, and okay, and also for the case of tit for tat that you mentioned, the total calculation of payoffs that you are doing there, it will depend on the initial choose of the strategy that is coming here. Na? Yes. If I first choose C, the sum will be different from that if I first choose D. So how to interpret that? And second question, how to prove these are coming as Nash? We commented tit for tat may come out as Nash equilibrium like that. Means.
Well, the fact that, say, if you, so tit for tat starts cooperating, the initial time cooperates, and then does whatever the opponent did the previous time, okay? Then in this case, if you are playing this strategy, I am playing this strategy, then we will always cooperate, right? And if tit for tat is playing against this strategy, then it will also cooperate forever, right? Yeah. Now, there is another strategy which is called tat for tit. I start defecting, and then I will do whatever you did last time, okay? And you can do the calculation and see that essentially if it plays against this strategy, it will not be a best response, okay? So in the sense that you could get a higher payoff against this strategy than tat for tit.
Just from the payoff matrix structure, you defined Nash equilibrium as the strategy pair from which there is no incentive to deviate unilaterally. Am I right?
Exactly. Yes, yes.
Now you have calculated some payoff for tit for tat as a summation process.
Yes.
Am I right?
Yes.
Now you claimed that this tit for tat may emerge as Nash equilibrium. Okay?
Yes. Yes.
Now how to be sure about that? I have got the summation, but now I want to know how to prove that this is Nash equilibrium.
Okay, okay. So it is easy to find that something is not a Nash equilibrium if you can find a different strategy which achieves a higher payoff against the same strategy. Okay? So, if in this case, it is not possible. It is easy to see that it is not possible because this is the highest payoff that you can achieve. There is no other there is no higher payoff that you can achieve, right? So if you think about it, say, every player, the sum of the payoffs here is 2 minus 2x, and the sum of the payoff here is 1 minus x. The sum of the payoff is 1 minus x. So here, say, the two agents are getting the highest payoff possible, right? So okay. How can you get a better payoff? Does this answer your question?
I was just, yeah.
No. Yes, you will not get a higher payoff.
Yeah, I will not
get. You will get the same payoff. Huh?
But if I choose some alternative strategy, there are 1,000 lakhs combination that I can take. So it will be very hard calculation to see that, no?
No, because this is just the maximum payoff that you can get. You cannot get a payoff up here. So this is the high. I mean, this is the best possible world when we both play cooperate. Okay, there is no higher payoff for both of us than this. Okay. Yep. Yes. The tragedy of the common is not repeated. It's not a repeated game. So the tragedy of the common is, well, for the others, the tragedy of the common is a game where there are a number of players which are like shepherds. Each one has to decide how many sheep to have, and they are grazing on the same field. And so, of course, the payoff of each agent increases with the number of ships, but also the quality of the food decreases with the total number of ships. And so there would be a social optimum number of ships so that the benefit that players get is higher. But the tragedy is that if each one decides how many ships to have independently, then they will end up choosing a higher number of ships so that this resource will be depleted and you really get... Now the thing is that tragedy of the commons is not is a single shot game. You can think of a repeated game, a repeated version of it, and probably. Yes. I think one can think about, say, using that. I didn't do the calculation precisely, but one can think about that, yes. Definitely. Yeah. Okay, so yes, sorry, that was a little bit quick. So you have to think about a game where the payoff is given by this. There is a cost for cooperation, and there is a benefit that you get from everybody else who is cooperating. Okay. Now, given this, you have essentially to think about this generalization of trigger strategies. Now, your opponents are n-1, okay? And you have to choose a subset of these n-1 players and decide which one to punish, okay? So your trigger strategy is that you will continue cooperating as soon as all these people cooperate, in this subset cooperate. As soon as any one of them defects, you will defect forever, okay? So if you think about... Yes, yes. Then if you think about this type of strategies, then you have to ask yourself, which are these subsets? How do I choose these subsets? And what you understand is that these subsets should be such that cooperation should, say, conditional cooperation should be reciprocal, and that there is a critical size of people with whom you should cooperate, and which is equal in this game is equal to this M. Okay. And that is a Nash equilibrium. You can prove it is a Nash equilibrium. Okay? Yes, yes, yes. It will be a Nash equilibrium in the sense that anyone has no incentive to deviate. Okay? Because essentially in this equilibrium, everybody is if all the people who are cooperating decide to defect, then any people that decide to defect will get a loss. Okay. Okay. So, but as we say, I would like to move to evolutionary games and say yes. As I told you, in evolutionary game there is a very different way in which we think about these problems, which is not a forward-looking way, and also it's a sort of a simpler way. So, so in game theory, you get a lot of, I mean, this forward-looking approach to game theory is very I mean, runs into a number of sophistication that I would just want to give you an example of this. So imagine that you have the following game in extensive form. So first there are two agents. One agent, so imagine there are two firms. One firm has to decide whether to enter into a market that is dominated by the other firm or not. So, and if this is the decision that firm one has to take, then decision to firm two, and if it decides to stay out, then gets a payoff of 1 and the other guy gets a payoff of 10. If he decides to go in, enter this market, then the second firm can just accept this and not fight, and they will share the market. But otherwise, she can decide to fight. And if she decides to fight, then the first player, now is the turn of the first player, he can again decide to stay out. And in this case, he will get a payoff of 0 and 0. But if he decides, of 5, so this is 2, this is 1 and 5, to be complete. I took this from the book of Ken Inmore. Okay. If he decides to insist in entering the market, then again, the second firm can decide either to fight back and to say accept this, and they will share the market, or to fight, and they will get a payoff of 0-0. Okay. Okay. Whatever the story is, these are the payoff, depending on what agents does or what the agents does, and you can look at what backward induction tells you. This is a game of perfect information, incomplete information. So you look at this, you go backward and you ask yourself, should player 2 accept or fight? So he gets 2 here and 0 here, so he should accept. Should player 1 try to get in or stay out? Well, here he gets 1, here he gets 2, so he should try to go in. Then you ask, in this case, should player 2 accept or fight? Well, if he fights, then he's going to get a payoff of 2. If he accepts, then he's going to get a payoff of 4. So he should accept. And here, player 1 should decide whether to enter or not, and then he will decide to enter, because here he gets 4, here he gets 2. Okay? So this is backward induction. Yes? Yes, here player 1 is choosing between going in, and then he anticipates that player 2 will, and so he gets 2. Yes, but this depends on what 1 decides. Okay? And if 1, so if you do backward induction, at this point, player 1 should choose to go this way. Okay, not this way. But this is exactly the point. So because essentially, when you are at this point, should player 1 really believe that player 2 is rational, so that he will choose this with respect to this? Because after all, if he has to make a decision here, so this is after player 2 made a decision which is not rational. Okay? So if he doesn't believe that player 2 is rational, then you see he may be scared that maybe he's going to end up here. Okay? And so maybe its best choice would be to choose out, because 1 is better than 0. Okay? And but if say 2 anticipates this, then it would say, well, okay, so if I do F, then this guy will doubt that I'm rational, will make this. So I actually better not play rationally, because instead of 4, I'm going to get 5. Okay? And now, so you see that you enter into a lot of, say, a conundrum of, say, rationality and beliefs and common knowledge of rationality. So this is, say, part of what game theory is about. Yes, you have a question.
Yeah. From the point 1, where from the picture starts.
Yes.
If the player 1 chooses to be out, then player 2 is getting 10. Am I right?
Yes.
So 10 is the incentive of getting the market.
Yes, but it's the payoff of player 2.
Yeah, for player. But market incentive should be same for both the players or not?
No, these are the payoffs. So if 1 decides to stay out, is getting 2.
Yeah, I'm not. Okay, player 2 is getting 10. That is right, na? Who is getting the market? He is getting 10.
Who is getting 10? Yes.
But when it is divided without any fight, why there is 4-4, not 5-5? That I want to know.
Okay, I mean, this is just. This is just a game. Okay, just to make the point that essentially there are situations which lead to a number of say very subtle issues about rationality and beliefs and all these things. But you should not take these numbers seriously. Okay. Okay, so let's go finally. I think it took. So yes, so okay, so let's go to evolutionary game theory. So, and this is a completely different way of looking at games. So it starts from the idea that essentially you think at a population of different of organisms of the same species, but with different phenotypes. Okay. And their reproductive success, which is their fitness, depends on the phenotype, and this phenotype, but also it depends on what other individuals they are interacting with in the population. Okay, so in some sense you could think that this phenotype, or which in the end goes, I mean, depends on the genotype. In your population, you will have different individuals who have made different choices of their phenotype or the genes, and you can think at this as strategies, and you can think at the fitness as the payoff that they are going to get when interacting in the population. Okay, so it's there is a sort of an analogy, and essentially the evolutionary game theory is about, say, making this analogy more precise. So let's discuss a very simple situation. Imagine that you have a population of beetles, and And this population is of small beetles, okay? And now there is a mutation and a variant of these beetles appears which have a considerably larger size, okay? So it is more efficient in getting food than the small beetles, but is much less efficient in processing food from the point of view of fitness, okay? Because in order to maintain a large body size, it has to eat more, okay? So you can think the following situation where essentially in a population where there were only small beetles, then the small beetles would reproduce with a fitness of 5. And if there are large beetles, interacting with large beetles, because they are less efficient in producing, because essentially they are competing with other large beetles, then their fitness is lower than the ones of small beetles, because essentially they have to maintain this large body size. Now, so if you were to think about only about the fitness of population in, say, homogeneous population, then you would say, okay, so there is no story. Then these large beetles are not viable. Okay, but actually you should think about what happens in a mixed population, where essentially there are some small beetles and some large beetles. You can imagine the situation where essentially every time these beetles have to look for food, they interact and they can meet a small beetle, can meet a small beetle and a large beetle, okay? And vice versa. And so it's like a game. So, and if a small beetle meets a large beetle, then the large beetle is much more effective in getting food. So it will get a payoff of 1, and the small beetle will get a payoff of, so the large beetle will get a payoff of 8, and the small beetle a payoff of 1, and the opposite happens. So these are, again, just numbers which are meant to just describe a, say, very stylized hypothetical situation. But you see essentially that, if this is the result of the interaction between these two different variants, and if the fitness of a particular variant depends on what is the fraction of the abundance of the different variants, then things can be more complicated, okay? And so one thing that you introduce in evolutionary game theory is what is called evolutionary stable strategy. Okay, so an evolutionary stable strategy is a phenotype or is a strategy that cannot be invaded by any other variants or any other strategies, okay? So what you have to think about is that, so let's see if S is an evolutionarily stable strategy. You should think of thinking about what is payoff or is fitness if there is a fraction L of if there is a fraction X of invaders, okay? So imagine there is 1 minus X of S and X, a fraction X of L. Let's say that X is very small, Okay. In this case, the fitness of the small beetles against this mixed population would be 1 minus x times 5 plus x times 1, so is 5 minus 4x. And what is the fitness of L in this population? So the fitness of L is 1 minus x times 8 plus 3 times x. So you see it's 8 minus 5x. Okay, so what you see is that in this situation where there is a fraction 1 minus x of this, fraction x of this, then the L will reproduce faster. Okay, so which means that the strategy L will invade. So S is not an evolutionarily stable strategy. Okay, if you instead do the calculation the other way around, and you ask yourself, is L an evolutionarily stable strategy? You can do this as an exercise, but you see that essentially if L plays, so now you should have a fraction x of small beetles and a fraction 1 minus x of large beetles. And you see that, because small beetles get anyway a smaller payoff, because again, this strategy is a dominant strategy in the analogous game. So the L cannot be invaded by S, okay? So in this case, we would say that L is an evolutionarily stable strategy, okay? And so you can think about, so you can now think that in situation like this, where you think about a uniform population with some variance inside, that evolutionarily stable strategy play the same role as equilibrium strategies which are played in the Nash equilibrium. Indeed, what you can show is that if if a strategy is an evolutionarily stable strategy, then the Nash equilibrium where the strategy is playing against the same strategy is a Nash equilibrium, okay? And actually, so all the states where evolutionary stable strategy is played against an evolutionary stable strategy are Nash equilibria. The converse is not true. So there are situations where you have a Nash equilibrium that is not an evolutionarily stable strategy, because essentially you see what an evolutionarily stable strategy implies is not only that the strategy should be better against the opponent, but also that when the strategy, when played against itself, should be better than the strategy, the other strategy, when played against the evolutionary stable strategy. Okay, so now I think time is running out, so I should. So, for example, if you take an example like this one, no, 4033. Then what you can check is that when you look at Nash equilibrium, you can ask yourself, well, imagine that L is playing, so player 2 is playing L, then the best strategy for 1 will be play L. If it's playing S, then player 1 is indifferent between playing S or L, okay? And you can do the same for player 2 and find out that Nash equilibria are this and this, okay? So these are the Nash equilibria because are the fixed point of the best response, okay? These are states where everybody is playing a best response to what the other is playing. Now, this is, you can show that this is, if you ask yourself whether both are evolutionary stable strategies, then what you find out that this is an evolutionary stable strategy, but this is not, okay? Because when you do this calculation here, so when L, let's say that you have a population where a fraction X of people are playing S and a fraction of people, 1 minus X of people are playing L, then here you would have that you get, from playing S, you get 1 minus X times 0 and 4 times X. Whereas here you get 1 minus X times 3 plus X times 4. So yes, no, this is an evolutionary stable strategy. Whereas, let's check S. So then I have to put, yes, I have to put 1 minus X and X. So now, if I want to check whether this SS is an evolutionary stable strategy, what I have to do is to compute the payoff of strategy S against this mixed population, which is 4 times 1 minus X plus 0 times X. And instead, when I play L, I get 4 times 1 minus X plus 3 times X. So you see that this is not an evolutionary stable strategy because in the population of L will grow, okay? Will invade the population, a pure population of.
Sir, yeah. May as you have defined the evolutionary stable strategy,
Yes.
only taking the case of pure strategies.
Yes.
Just I want to make some comments here. First, the thing is that if any strategy that is Nash and pure Nash, pure strategy,
Yes.
that must be an ESS, evolutionary stable strategy. Pure Nash must be ESS.
No. I mean, this is a case where this is not is a Nash equilibrium pure strategy, but it's not an evolutionary stable strategy.
But maybe, but as per whatever means in the literature, it has been proved that pure Nash, pure strategy Nash, must be an evolution.
Strict Nash equilibrium.
Strict Nash, yeah, strict Nash, exactly, exactly, yeah.
An equilibrium and evolutionary stable
Stable strategy.
It is true.
Yeah.
So this is a Nash equilibrium which is not strict.
Okay.
In the sense that if So this is a strict
Yeah.
equilibrium.
Yeah, means
Wait a moment. No. So this is not strict, because you see that in this state, player 2 is indifferent between plane S and L. Okay? In this equilibrium here, player 2, if instead of playing S, plays L, gets the same payoff. Okay? So this is not a strict Nash equilibrium, it's a Nash equilibrium where any deviation incurs a loss, a positive loss in utility. Okay? Instead here, you see that player 2 or player 1 can deviate and play L, but he will still get 4. Okay, so this is not a strict Nash equilibrium, and it's not even an evolutionary stable strategy.
so strictness must be ESS. Only strictness must be ESS.
If it is strict Nash, it must be ESS. But if it is not strict, it may not be ESS.
So pure strategy may not be strict Nash. Pure strategy Nash.
So the strict Nash equilibrium implies ESS, and this implies Nash equilibrium. Okay? So the opposite is not true. Okay? So the opposite of any of these is not true. So if here you have a Nash equilibrium, but it's not an ESS, and so it's not a strict Nash equilibrium. Okay?
So I'm just asking, any pure strategy which is Nash, that may not be strict also. Pure strategy case, if the pure strategy, if you say this is a Nash equilibrium, can that be the case that is not strict? That I'm asking. Because...
So you have evolutionarily stable strategies, equilibrium evolutionary stable strategy, which are not strict.
No.
And every equilibrium in mixed strategies is an evolutionarily stable strategy equilibrium, but it's not strict.
No, I'm not saying that. I'm saying that ESS must be a strict Nash. That's.
You're saying that this also must be true. This is what you're saying.
No. Okay, I'm just telling for a pure strategy which is Nash.
Okay. If you're saying for pure strategies, then if you're saying for pure strategy then strict Nash equilibrium and ESS must be the same, then I think you are right. Yes. But there are equilibria of mixed strategy ESS equilibria which are not strict.
Exactly. Okay. That I'm telling. Yeah, exactly.
Okay. So we agree. Okay, thank you. Okay, so indeed, say you can generalize this to mixed strategies, and essentially the way you generalize this by saying if you have a strategy where player 1 plays one strategy with certain probability and the other strategy with the other probability against another mixed strategy in general, then again this mixed strategy is an evolutionary stable strategy if it cannot be invaded by any other strategy, by a fraction x of any other strategy Q, for any Q, okay? And but the argument is essentially the same. So what I think since time is over, I would just like to make an important remark. That essentially you can so the idea about this of this evolutionary game theory is that in the end you are thinking about population whose fitness is proportional to this to the payoffs, and so you think that the number of individuals in each population increases with a rate which is proportional to the payoff that they get by playing their strategies. And so the number of individuals with a given strategy, Si, increase with this rate. And this rate essentially depends on what other strategies is played in the population. So, so you have a set of equations for the rate of growth of the different populations. And if you write down the equations for the fraction of this the fraction of populations that play a given strategy in the fraction of individuals that play a given strategy in the population, then you get this replicator dynamics. You get, and in the simplest case where you take the fitness is just proportional to the utility, then this replicator dynamics takes very simple form, which is that xi is equal to, x of strategy S is equal to x of strategy S times the expected value of the payoff against other strategy which are played in the population, minus the expected value of the average payoff in the population. Which is this one. Okay, so the only point I wanted to make is that given the game, this equation, if you solve the dynamics for this equation, so these are the probabilities, so they should be normalized to 1. And if you solve this equation, what you get is that the dynamics converges to these evolutionarily stable strategies. So the point to which they converge. So the only point I want to make is how you interpret the case where it converges to a pure, a mixed strategy, okay? You can interpret it in different ways. As each member of the population playing a mixed strategy. So as you have, so in this case, you should interpret it as the fraction of people playing, the fraction of individuals playing a given strategy converging to the mixed strategy. But you could also think about, say, a situation where agents, you have a number of agents, and these agents are paired in match randomly to play this game in pairs. And you could see how their population increases, how their mixed strategies evolve. And so what happens is essentially that if you do the things carefully, what you find out is essentially that doesn't matter, okay? Even if you think that even if you think of individuals of this population being composed of individuals that play mixed strategies and that they evolve over time according to this dynamics, then in the end, the the dynamics will converge to one where each subpopulation will fix which each individual will fix to play just one strategy. And the fraction of individual playing the strategy is given by the mixed strategy. And this is something that Sanjay has worked on some time ago. So I think we are. So if you want, I can give you during the coffee break, for those who are interested, an example of this, an example of a game where, with an intuition of why you get convergence to pure strategies in population games where of this sort. Okay.
Just to, I've got one question about dynamics and one question from the game theory part. Just to come out of confusion, I'm making some comment. Whether I'm right or wrong, please tell me. Given a Payoff matrix, if I'm allowed to have mixed strategy, I must have at least one Nash equilibrium. Right or wrong? Yeah. Now, there may be pure strategy Nash, may not be, or there may be mixed strategy Nash, may not be, but there will be at least one Nash.
Yes.
Now, if there is a pure strategy Nash, that is a very crucial comment, maybe I'm wrong here, just asking whether it will be a strict Nash by default or may not be for a pure strategy.
If there is only one.
Yeah.
If there is only one, I think, and there is no mixed strategy Nash equilibrium.
No, suppose there is only one pure strategy Nash equilibrium.
Yes.
It must be strict or it may not be also. That is my question, first question.
So look, we can discuss about this. I'm not sure.
Okay.
Whether what is I'm thinking about this example, and you could think at situations where if I replace this 3 by -3
exactly, we have to check probably that.
And probably that is a Nash equilibrium which is not strict.
Okay, we have to check that.
Huh?
Okay, we will check that later after the class. But the fourth question, if that is a strict pure strategy Nash, that must be an ESS.
Yes.
Okay. And for a mixed strategy, we have to check whether it is ESS or not. There is no rule. Okay.
Yes, for a mixed strategy Nash equilibrium.
Exactly.
Yes.
So there is no rule. We have to check it by the rule that you have sought.
Yes, in 2x2 games, you have that. Yes, you're right.
Yeah.
Yes.
Now I come to dynamics.
So depending on you could have that when there is only one in 2x2 games, when there is only one Nash equilibrium,
Yeah.
then a mixed strategy Nash equilibrium, then it's ESS. When there are also pure strategy Nash equilibrium, then
we have to check then. Then the dynamics. Suppose we converge to a point where there are two phenotypes, x1 equal to 0.2 and x2 equal to 0.8.
Yes.
Converge to that point. Now, you already told there are two interpretations.
Yes.
One interpretation is that everyone in the population is choosing 20% probability strategy 1, 80% probability strategy 2.
Yes, exactly.
Second interpretation, 20% of the population is choosing strategy 1 and 80% the strategy 2. Yes. Why these two different interpretations and which one is valid?
So the second is valid in the sense that if you think about the real game being played, so every agent never play the game against himself. So the way in which these population games are played, I mean, the idea you have in mind is that you have a population, you pick up two guys, and they play the game, okay? They get their payoff and they reproduce, okay? So now, when you do this thing, and you imagine these two guys play mixed strategies, okay, the dynamics that you have on the left-hand side here, if you take the dynamics of agent alpha, Okay, is so of strategy S divided by PS. Okay, this is a function that does not depend on PS. Okay, so this cannot converge to an interior point. It either converges to a corner. This is what Sanjay has shown. Okay, so whenever in this equation you have a mixed strategy Nash equilibrium, you want to interpret this XS as 1 over n sum over alpha of say mixed strategy of agents, of different agents. Then when you write the population dynamics or the equivalent dynamics for the individual agents, that you can also interpret as learning dynamics. Then you find out that because agent alpha does not interact with himself, then this is an equation where this is constant with respect to P alpha, so you cannot have interior solutions.
Okay, so you are saying second interpretation is valid.
Yes.
But if I see from the Nash point of view, he did not know dynamics. He only took the Payoff matrix and calculated what rational outcome is going to be. Then for that case, when Nash did just for one shot game, one game playing for the single time.
Yes.
Then how can we interpret x1 equal to 0.8, x2 equal to 0.2, this kind of things?
No, this is really here. What I'm thinking is not a two-player game. So here I'm thinking at a game that is played by a large population of people that meet at random in pairs. Say the two pairs are drawn at random, and they play this game, and they reproduce accordingly, or they update their strategies accordingly. Okay.
For a single shot game, I just want to ask, for a single shot, one game just played for one time, only one time. We are finding mixed strategies, stating the strategy is x1 equal to 0.2, x2 equal to 0.8. So for a one shot game, what does this mean? Means player one is choosing with 10, 20, I am choosing one strategy, one of the two.
Yes. No, it's okay. So say if you so if you take the situation where all these P alpha are equal to X, then of course this is equal to 0, okay? But if you are looking at stable outcomes, where this dynamics will converge to, this is an unstable state, okay? So you can still think that this is a Nash equilibrium, but this is not a strict Nash equilibrium. It's not an evolutionary stable state. It's not an equilibrium in evolutionary stable strategies. Okay? Does this clarify? Then I think